Hi everyone. It's about time for some more lectures for the astronomy classes. We're going to finish up with a couple of videos on some of the ideas about light and waves. The first thing we're going to talk about is something we're all familiar with. Well, maybe not so much in Southern California, but if you live other places, you commonly see this, and that is you'll see a rainbow after a heavy rain. This beautiful idea of rainbows, and that's where the light from the sun is basically spread out. We call it dispersion, spread out into its different mixtures of colors that you can see every color of the rainbow as light passes through raindrops. And so rainbows really brings us into something called the science of spectroscopy. Spectroscopy. Amazing I can spell, right? And so with this idea is how we can find different types of spectra, that's plural for spectrum, spectra, plural for spectrum of colors. Those are all the basically individual colors, pure colors that make up any type of light we see. So the most common one is where we have white light. White light is made from all the colors of the rainbow. And when they basically mingle together into what we can see, we see white light. And so that's one type of spectra. And it turns out there's 3 different types of spectra. And what we say is these are the 3 Kirchhoff laws of spectra. And so what we're going to do in this bit of our lecture is go ahead and describe these 3 laws. And we're going to go ahead and describe basically where we get these different colors that make up a particular spectrum of the 3 types that we can find in nature. And, basically where do we see them in nature and how we use them in astronomy. The very first type brings up what is known as a continuous spectrum. And a continuous spectrum has basically all colors present. All colors are present. And generally what we find is that we have a very dense, hard object, and it's very hot, and because it's hot, it glows with many different colors. So it glows with light, and if you see it, it generally looks like white light. And if I put something like a crystal, we'll call this a prism. Prism's kind of like the crystal that may be hanging off of your mirror in your car, guys. The mirror that's, the little crystal that hangs off your mirror, that when light passes through it, it basically produces a rainbow of colors on your cowhide seat covers of your car. You've got that crystal hanging from your mirror right next to your big dice, right? And so maybe you've seen this before, where you see a rainbow of colors because of a little crystal of glass. Prism acts the same way. When light passes through that prism, it basically spreads it out or disperses it into the individual colors of a rainbow. And when you have a dense hot body, when the light comes out, I only have a few colors here, what would happen is we would get red light of different shades. We would have basically blue lights of different shades, and violet, and green, of course. Well, that's not green, but you get the idea. And then orange, and then different shades of red. So anyway, the whole point here is we have this idea here of how light can be spread out as it passes through this prism. And we would see every color of the rainbow. So what's happening here? Well, the electrons found within this are basically jiggling around, and as they vibrate in different directions and different speeds, they'll produce different colors. You know, back to the old EMN rule that any accelerated electrical charge loses energy by producing light, and that light color depends on how they're being accelerated. So if I asked you on an exam, what produces a continuous spectrum? A very hard, dense object. Where do we see this in nature? Those old-fashioned incandescent light bulbs is a good example of this. What you have in this light bulb is you have in a glass globe, that basically is evacuated with air. You'll see a very hard, dense material. It could be tungsten. It's a very hard, dense metal. It gets very hot. And because of that, all the electrons are jiggling around on this. It produces every color of the rainbow, and also it's a white color. And that's why incandescent light bulbs are comfortable to see with. It really kind of reproduces what our eyes are accustomed to when we go outside and look at the world under the light of the sun. Incandescent light bulbs are very comfortable. And so one of the slides you'll see is this one right here. You'll see, you know, a light bulb that has that hard, dense, filament. The light comes through, passes through a filament, through the prism, and then passes in until you finally see on the screen, on the right side, you'll see all the colors of the rainbow, the continuous spectrum. And so that's the first type of spectra or spectrum that you'll see, a continuous spectrum. The next type is related to how atoms can have their electrons excited to higher orbits, and then the electrons drop back down. And to do that, first off, the electron has to gain energy to jump up to a higher orbit. So this is the nucleus right here. Okay, and you have the orbits. And we've talked about this. There's an electron here. And if it gains energy, you can hop up to a higher orbit. It doesn't like that because it means that the atom's at a higher energy level, because if this is orbit 1 and orbit 2 and orbit 3, the energy of the electron in orbit 3 is more than the energy of the electron in orbit 2, which is more than the energy of the electron in orbit 1. So when that electron absorbs energy by some means, and it hops up, it has to lose it. So it can drop down to step and then step, or it can drop all the way down. You'll produce photons of different frequencies or wavelengths, is another way of saying it, and different colors. But there's a rule. Atoms can't produce every color of the rainbow. They'll produce individual, very bright colors of pure light. And of course, when you mingle that together, it can look, you know, like a beautiful lamp. But when you spread the light out, instead of seeing every color, you'll see individual colors. So as an example, and I'll talk about this a little bit more, what we see here is where light's been produced, but you only will see, let's see if I can get it in there, only individual colors that you'll be able to see on this slide. So let me go through Kirchhoff's law and I'll explain it to you. So this is for the second type of spectra. And so this is known as the emission or bright line spectrum. So what we have here, so you might have a low pressure gas of different types. Maybe it's a hydrogen gas. And because it's hot, so this is a hot low pressure gas, maybe hydrogen in my example. Because it's hot, it's going to glow. Now if I put my prism here, instead of seeing every color of the rainbow, I may see a particular blue color or violet color. I might see a nice green or aquamarine type of green. Now that's not it. I did that again. I don't have a pen here. Imagine that's green. I'll grab one. And you might have a nice red. And so those colors basically are only the particular colors that you'll find for hydrogen. Every one of those colors, remember, is given by their wavelength or frequency. And so what we said before is that red light has large wavelength. Lambda means wavelength, remember, review that. Blue light has small wavelength. And so which colors are produced depends upon the atom. Now what's cool about this is that since every atom produces its own emission spectrum, every atom produces its own emission spectrum, if we see the patterns of color that belongs only to that atom in the light coming from a object from space, we know that gas must be a part of that object. So really what we're saying is that the emission spectrum are like fingerprints. You know, everyone that has a fingerprint taken, your fingerprint will be completely different than any other human that's ever been on Earth. And so they're identification for you. In the crime, if they find your fingerprints, you did it. Well, if we find the fingerprints of the atoms in the terms of the types of color we have here, then it gives us a means of identifying what an object's made from. I mean, how do we know what stars are made from? How do we tell what an individual star actually is made out of? No one can go there and take a sample. We can't even go to our sun to take a sample. If you go there, you'll be vaporized. Or if you get there too close and didn't get vaporized, you'd be squashed by the gravity. If you got there and still didn't get squashed or vaporized, you'd be destroyed by the radiation coming out of the sun. So there's no way to go there to take a sample. The way that we do the chemical analysis of the makeup of an object is by looking at the individual colors that can come out of the gases found within a star. So if I ask you what type of material makes an emission spectrum, it's a hot, low-pressure gas. Where's an example of that? If you ever see a motel or something that says vacancy or no vacancy with that neon lamp, what you have in that glass light fixture is a low-pressure gas, in this case made from neon. You pass an electrical current through it, which basically heats the gas and allows the gas to gain energy, causing the electrons to hop up to higher orbits. When they come back down, they produce individual colors that when they mingle together, you'll find that it generally has that kind of nice reddish orange look of a neon lamp. Of course, there's other types of neon lamps also, and those are made by different gases and mixtures of gases to produce the tone of the color that when we combine all the individual pure colors of that gas, gives the hue of what we see of the sign. That's a real science. It can be expensive. So if I ask you this, how do we know what a star is made from? It's from the emission spectrum by looking at the pattern of different colors. Now remember, there's different shades of blue and red and orange and green and so forth. How do those shades vary? They vary by wavelength and frequency, but not by very much compared to how red light will vary from blue light, as an example. They vary much greater in wavelength or frequency than the different shades of red, where they vary just a little bit. But what's astounding is our eye is so sensitive to wavelength that even though the wavelengths don't vary by a whole lot, we can discern and determine the variations of color for different shades. It's kind of amazing. So that's the second of the three types of spectra. There's a third type. And this is kind of like a combination of types. And so what we have here, we might have a hard, hot object. Hard and hot. And remember what we said on the first type of spectra? A dense, hard, very hot object produces every color of the rainbow. And then in front of that, we may have a cloud of low pressure, but now not hot, but cool gas. Say it's hydrogen. Now what we said is with that gas, a low pressure gas being hot, it would glow, and therefore we would see bright lines of color. But this is cool gas, and we have a hard, hot object, light glowing out and passing through that cloud. And so what occurs then is that the light from that hard, hot object passes through. I put my prism there, and what I see, it's hard to do this, I would see every color of the rainbow, so that's all colors of the rainbows, but it's going to be missing certain colors. Let's say that this is hydrogen. Remember we said that hydrogen produced a nice pretty violet color. It produced a really pretty aquamarine or a greenish light, and it produces a really nice violet. Well, because it's cool, those colors will be absorbed by that gas, meaning that the atoms like that color for the energy that they represent because of their frequency or wavelength. And therefore, we would see every color pass through that cloud of gas that's cool, coming from that hard, hot object, except for the individual colors that would normally be the emission spectra for that gas. And so we see all colors except missing colors. We miss the violet and the aquamarine and the red. Those are missing colors. Now remember what we said on the second type of spectra, the emission spectra, we saw lines of color. And so those are known as spectral lines, those lines of color. These are absorption lines, meaning that light's been absorbed by the cool gas coming from the hard object. And so this type of spectrum is known as an absorption spectrum, just light's being absorbed. And just so you know, if I asked you what type of light would I, or what type of spectra would I see with a star? What I would see is this type. So stars produce this type. So when you take and look at a spectrum of a star, what you'll see is every color but many, many missing colors. And what a person that studies spectra does is they have to take and look at all those missing colors, and they can determine the wavelengths of what those missing colors are, and then take it back to what gas must be present in the outer portion of the star that would absorb it, in this case hydrogen. And so that's a very complex thing because there could be thousands of absorption, dark lines in all the colors of the rainbow of a star. And so it's very detailed work, but with that, they can determine basically what a star is made from. And so from that, we have 3 different spectra. If I ask you what type of spectrum does a star produce, it's the absorption spectrum. If I ask you what produces that, there's a hard, hot, dense part like the core of a star or in the inner portions of a star, surrounded by a cooler gas that's like in the outer portions of the star. And out of that comes all colors like some missing ones. It could be that it's the, just a hot, low pressure gas like a neon light. What type of spectrum is that? That's the emission spectra. If it's like an incandescent light bulb with a hot filament inside so bright, you would see white light coming from that or every color. Just to show you, this is the absorption spectra. We have that hot, very, very dense and hard object, the incandescent light bulb, the light passing through a cool gas. Out of that comes every color except some missing colors. And the missing colors is related to what that cool gas is made from. And those missing colors are absorbed by that cool gas. And that's the type that we'd find in a star. So that's one of the topics we have to speak of. I'll bring you a second lecture very soon. See you soon. Take care, guys. Hope you're doing well.